All right, this is going to be a screencast that will introduce you to atomic physics. And when we're back in class, we will kind of pick up where this leaves off, but this will keep us moving forward as we are out of school for distance learning. So I just wanted to get started with this intro over the weekend. So we're going to start chapter 28. It's kind of the next phase of modern physics where we're going to talk about the atom and the structure of the atom, which was another major area of experimental investigation in the early 1900s as they started to be able to have instruments and methods to be able to examine matter on a smaller and smaller and smaller scale. And they started to develop new experiments. They started to learn more about the atom itself. So we're going to talk a little bit about what different models of the atom existed prior to 1900, and then kind of the series of changes that came about in the early 1900s to settle on what we basically understand as the structure of the atom today. So what's new in this chapter, remember in the last chapter we talked about cathode ray experiments. That was actually the experiment where you heated up the cathode side of a negatively charged plate really hot, and it ejected electrons because they gained enough kinetic energy, and they created a beam. They called them cathode rays, and they realized they were negatively charged. They actually discovered the electron through that process. So they figured out what the charge to mass ratio of the electron was from that process, which was a big deal because they realized that it was the charge to mass was 1,000 times greater than some other things they had observed. So they realized it either was really highly charged or very, very light. So it turns out it's very, very light. But since most forms of matter on Earth are neutral, there has to be an associated positively charged particle that hadn't been discovered yet. And we're going to understand more about how they discovered the proton and the neutron in this unit and how we began to understand the structure of an atom. So early atomic models, we learned early in the year, I think it was when we were talking about thermodynamics, we talked about a piece of paper that was wet, that was evaporating, the moisture was evaporating on it. And based on an analysis of the way that the moisture evaporates off the paper, that matter must be made up of tiny little particles. So the particles they freely move inside conductors, but they don't inside dielectrics. So scientists want to understand this, and that's what motivated some early models. That's what explained some of the early models of the atomic nature of matter. So they were trying to explain this behavior of freely moving negatively charged particles. The first, there was a billiard ball. Before Thomson, there was a billiard ball model of the atom that was basically like all elements are made up of just solid little billiard balls that had a positive and a negative charge that offset each other. That was prior to the plum pudding model, which was in the late 1800s. J.J. Thomson said that basically you've got these negatively charged components in atoms that are equally distributed inside this pudding that's positively charged, that offset the negative charge and made the atom itself neutral, and it was kind of a uniform density kind of thing. So that was a model that explained the behavior of some of the things they had seen. And so Ernest Rutherford, who was an Australian, developed a new model of the atom. And we're going to talk about his experiment because Rutherford's experiment, you may have actually seen it in chemistry class. It's a pretty famous experiment with gold foil. And he developed the model based on his experimental, based on what he had done in the lab, that there was a tiny nucleus that was really, really dense that contained most of the mass of the atom, and all of its positive charge was collected there. And that was based on his experiment using gold foil. So the plum pudding model, you would have expected in the plum pudding model a different result than what happened in Rutherford's experiment. So let's explain Rutherford's experiment. You've got a piece of gold foil right here. Actually, I'll move over here. There's a piece of gold foil right here. And there's a source of alpha particles. Those are helium nuclei. So alpha particles are the nuclei of helium, so it's like 2 protons. Because remember, helium has atomic number 2, and the nucleus basically has only 2 protons. So he was shooting protons through this gold foil, and then there was a detector to detect where the alpha particles pass through. If there's a little angle, if it encounters some other substance inside the plum pudding atom, it's going to kind of ricochet off an electron or just pass through the plum pudding straight through. So given that model of the atom, if the plum pudding model, the Thomson model, was accurate, you would expect to see all of those helium nuclei, the alpha particles, to pretty much collect at one place on the far side. So the detector would see this big spike in collisions of alpha particles, carrying through the plum pudding. But what actually happened was way different. There certainly was a lot of alpha particles that collected on the far side towards the center, on the opposite side of where they were being shot from, which is over here. But they were also deflecting at kind of big angles, and some of them at really big angles, way out here. And then some, really surprisingly, came almost straight back. Not very many, very small number, all right? The vast majority went right through, but there was nothing in the plum pudding model that would explain why some of them came almost straight back or deflected, at extreme angles like this. So that experiment by itself required kind of a new understanding of the atom and trying to figure out what the structure of the atom was that would, a model that would support that experimental result. So what resulted from that is Rutherford's planetary model of the atom. So he envisioned this positively charged nucleus that was really, really dense, and electrons that orbited around this nucleus. So it still met the requirements that it was a neutrally charged atom. So you had the positive and the negative charges, but instead of the positive charge being kind of dispersed in this pudding substance, it was now collected in the nucleus. And the electrons were orbiting this nucleus like, the Earth orbits the sun, like the moon orbits the Earth. So, and we know from our studies of orbiting objects in AP Physics 1 that if you know the distance r from the nucleus and you know the force it wants to pull it in, which in this case is an electrical force, it's got to have some kind of tangential velocity, and it's got to have a pretty high tangential velocity to keep it orbiting in a perfect circle around that nucleus. For the Earth and the Sun, this red arrow, this force, is a gravitational force, and there still is a gravitational attraction between an electron and a proton in the nucleus, but the electrical attraction overwhelms the gravitational attraction. Remember, by a factor of 10 to the 40th power. It's much, much, much stronger. So the velocity of the electron going around the nucleus would have to be really, really fast to be able to sustain that circular orbit. So that was a model that had a problem, inherently had a problem, because an electron is a charged object, as you know, and when you accelerate a charged object, which going in a circle is an acceleration, even though it's constant speed, it's changing direction every instant. So technically, it's an acceleration, it's a charged object. You know that would cause an electromagnetic wave to be emitted, electromagnetic radiation. And when that energy is emitted, when that wave is emitted, it is carrying energy with it. That's what an electromagnetic wave is. Based on the frequency of that wave, you know that's the energy associated with it from Planck's equation. So if the electron were to lose energy at the rate that it the electromagnetic theory predicted at that time, it would spiral into the nucleus really, really quickly, like in microseconds. So the Rutherford model couldn't explain how atoms were stable, because clearly this isn't what happens. That's not what actually happens. Electrons don't spiral into nuclei. So there needed to be a better explanation of how atoms remain stable. But clearly there was a very dense nucleus based on the gold foil experiment. So there needed to be some more work done to try and understand this. So at the same time, you know that black body radiation was being studied by scientists, and they understood that objects could emit electromagnetic radiation in the infrared spectrum based on their temperature. At the same time, scientists were studying the emission spectra of low-density gases. So instead of a solid black body solid object that was in the solid state of matter, they were looking at very low-density gases, and low density so that there was not much interaction between individual molecules. Gases are already molecules are spaced really far apart. Well, if you make it a low-density gas, very low pressure, you even space these molecules out even further. So you're looking, when you study low-density gases, you're studying interactions at the atomic level only, not the interaction between individual atoms. So they were looking at low-density gases. They were heating them up, and they were shining a light through those low-density gases. And what they saw was called an emission spectra. There's actually two different things. There's an absorption spectra, which is actually what I just described. When you shine a light through a heated gas, you get an absorption spectra. When you heat the gas up and just look at the gas through a diffraction grating, like this guy right here, like we've already seen in our class, you actually see the diffraction grating causes the light that comes from the gas to bend. You actually see these little bright lines in the visible spectrum of all different colors. And what scientists understood was that each element had its own unique emission spectra. So when you took hydrogen, for example, and took low-density hydrogen and put it into a tube, and you heated that tube up, you could either heat it up temperature-wise, or you could put a really strong voltage, an electric field, across the two ends of the tube, and the gas would glow, and it would emit this spectra. When you looked at the glowing gas through a grating, you would see this emission spectra. And every element had a unique emission spectra. So these bright lines were unique to each gas. It was kind of like a fingerprint for an element. And each one of those bright lines represents a wavelength, a specific wavelength of visible light. So you can see the red ones on the furthest outside. Those are closer to 700 nanometer lengths. Let me just point those out. So these are like 700 nanometer wavelengths, longer ones, which deflect more. Remember our red laser, when we shone it through a diffraction grating, that's the one that deflected the most. As you get towards the center here, the central maxima, you see the blue or the violet, and those are closer to 400 nanometers. They deflect less. But each element had different bright lines, of different colors, different wavelengths. So that was perplexing, and there was no explanation for this. So at the same time, scientists are trying to understand the structure of the atom. They're studying the emission spectra of gases, and they're seeing this strange behavior that they're trying to explain. So it turns out hydrogen was studied the most because it's the simplest gas. It has only one proton and one electron, no neutrons. So hydrogen was a really popular one to try and understand the structure of the atom, because we knew it was a very simple spectra. I guess we didn't know that there was a proton in the nucleus at this point, but it was a simple emission spectra. So this is the emission spectra of hydrogen gas in a tube when you put a high voltage across it. you see these particular bright lines. And you see that there's a red one over here. That's at about 656 nanometers. Then you got a few others, and then the shortest wavelength one that you can't actually see because it's in the ultraviolet spectrum is 364.6 nanometers. That's in the UV spectrum. The last one that's in the visible spectrum is this violet one around 402 nanometers. And so it turns out there was a guy who was a high school physics teacher, believe it or not, in, I think he was Swedish, Johann Balmer, and he was able to see a pattern in these particular numbers, which seemed like totally random to us, 656.3, 486.1, 434.1. There doesn't seem to be a pattern, but he was able to come up with a pattern, and I see my, oops, sorry. My slide here got rid of some of the symbols. That's the equation. So he came up with an equation that actually modeled these wavelengths. R is a constant called the Rydberg constant. So that's a fixed number. And n is an integer 3, 4, 5, and 6 for those 4 lines. So just kind of a weird math equation that this individual, this scientist in 1885 came up with that was able to predict the location of these, the wavelength. So 1 over the wavelength, I should say. Here's the wavelength. For example, the 656.3 would be the longest wavelength. So we want what's inside the parentheses to be the smallest. So you want to subtract the largest number from 1 over 2 squared. So that would be smallest denominator. So n equals 3 would correspond to that wavelength, I believe, if I'm doing my math right in my head. The point being, you could solve this for wavelength after you substitute those integers in, and you could predict, you would get these actual wavelengths here. But it didn't explain why. It was just a mathematical concoction that this guy came up with, and it was able to very accurately predict mathematically where those were, but there wasn't a model of the atom, of the structure of the atom, that was consistent with this mathematical equation. So where I'm going to end today is just kind of the first introduction of Niels Bohr, because Niels Bohr is the guy that came up with the structure of the atom that was able to explain what Johann Balmer's little equation was. He was able to talk about allowable energy levels. His model predicted allowable energy levels in the atom, which you guys learned when you took chemistry. And if you had AP chemistry, you're probably really familiar with it. So we're going to pick up on Bohr's model of the atom on Monday, and we'll go from there. So guys, have a great weekend. Thanks.